Let me now try and look at this tunneling effect in a bit more detail in terms of the potential energy that is experienced by the electrons. Right, I'll start by drawing the needle in a slightly different position. Let's say let's say I have the surface of the sample, the copper sample, this way. So that's the copper surface, and the needle, I have the needle, say, this way. So this is the needle, and we move the needle this way. Okay, and there's the tunneling current goes through here. That's the tunneling current. Electrons. Right, I'm going to talk in terms of conventional current. So I'm just going to say that the electrons flow this way, sort of jumps through the gap in the vacuum. So that's the vacuum. Now, in terms of the potential, what does it look like? Each atom here, we might imagine that each atom here has a potential. Now, I'm going to try and draw a graph of this. So let's say I have this axis. This is the x-axis, this direction, and my vertical axis is, say, the potential energy of the electron. Now, in the vacuum, the potential energy is 0. It's just 0 there. It's green here to represent the potential energy in between. Now, for the atom itself, has potential energy, which is given by this formula, the Coulomb's potential. U is equal to E squared over 4 pi epsilon naught R with a minus sign. The R is the distance from each atom. Let's say there's an atom here. Then the distance from the atom would be the distance from this point, and the graph of this would be the graph of 1 over R. So each of these atoms would have its own potential energy given by this formula. So let's say I have another atom there. It would have its potential energy would be given by this 1 over R graph around that atom, and an atom further away would have its own potential energy graph. Okay, but when we have lots of these atoms together along a row, we would expect that the potentials would add. So when this potential curve and this potential curve add together, we get something like that. The last one has nothing to add, so it goes right up to the vacuum level. Okay, so lots of these potentials adding, and so on and so on. And on this side, this is the vacuum, the gap in between. And then when we reach the copper surface, the atoms in the sample itself, let me write this. This is the needle. Let's say this is the tungsten needle. This is the copper. copper surface. So the surface, the copper is a sample that I want to image. I want to look at the atoms of this copper. So as we imagine a line going into the copper surface, each atom along this line will have its own Coulomb potential given by this 1/r formula. Alright, so just like in the needle itself. So we would expect the same adding when they overlap. So I'm just going to draw very roughly. What the combined effects of adding all the potentials of all the atoms will look like. Something like that. Now, if I have an electron in here, if we imagine one electron, one of the conduction electron here, this conduction electron would be able to move freely around, and let's say this level here represents the total Ke plus Pe of the electron. Ke plus Pe of the electron. P is given by this graph here. So the Ke would be, it's depending on its position, would be given by the distance from, let's say the difference between this level and the potential energy graph. So as the electron moves towards here, let's say because a voltage is applied between the needle and the surface, this voltage could cause the electron to try to move in this direction. But when the electron reaches the tip of the needle, which is around here, it would experience a higher potential as it reached the edge of the vacuum. Reach a higher potential, and as it tries to move against this potential, it would quickly use up its own kinetic energy, as I've described maybe 2 videos ago in the quantum tunneling video. So as it tried to move towards the vacuum, it would use up its kinetic energy, because this final atom at the tip of the needle would try to attract the electron back. So the electron would try to do work against the attraction of that atom. Okay. So as it tries to move away, its kinetic energy would be used up against the attraction very quickly, before it even leaves the vacuum. Okay. Unless we have a huge voltage, which we don't. It's usually maybe just a few volts that is applied in the scanning tunneling microscope. So what happens when the kinetic energy of the electron is used up? Well, let's see what happens. So we have this wave, right? This electron, if you think of this electron as a wave, so we have this wave arriving at the barrier, at the potential. So this potential is like a barrier. It prevents the electron from going through it. And because when the electron tries to go away, we have to do work against potential and use up its kinetic energy. So it gets stuck here. But because the electron is a wave, the wave cannot just get cut off here. Because if it does, if you remember, the wave suddenly get cut off to 0 here, this sharp change in the wave function, in the wave, would mean a very huge energy, would mean that there's a very huge energy involved here. So because of this, because of energy conservation and the wave nature, we have to have the situation would force the wave function to change smoothly into the barrier. Okay, so that it doesn't drop to 0 immediately. And if it changes smoothly into the barrier, it would slowly die down, slowly get smaller and smaller, decrease in amplitude, right, as it goes further and further into the barrier, because it gets less and less likely to exist with no kinetic energy or insufficient kinetic energy. So the amplitude of the wave would just die, would decay like an exponential function. Now, but in the case of the scanning tunneling microscope, the gap between the vacuum between the tip of the needle and the copper surface is quite small. Maybe, I don't know, maybe just 1 or 2 atoms apart, or very few atoms apart. So before this wave function dies down to 0 completely, where there's still some amplitude left, the wave function would have reached the copper surface. So this tail of the wave function arrives at the copper surface with maybe a smaller amplitude, but not zero. Right? So as a result, the moment this wave emerges into the copper, the moment it reaches a point where its kinetic energy can reappear, right? Because when it reaches here, the potential inside the copper becomes negative again. Alright, or not negative again, but okay, the potential inside the copper is always negative. I mean, the potential experienced by the electron becomes negative again, so that its original kinetic energy can reappear, okay, to be non-zero. And once that kinetic energy is non-zero, it can then start having a velocity like before, like the velocity that it had here. So what velocity it has here would then more or less reappear here. Maybe not exactly the same, depending on how big the potential here is compared to that. But there will be a velocity, and the electron can continue to travel again as something like a sine wave. Again, maybe not exactly a sine wave, but it can continue to travel on. So essentially, that's how the wave actually behaves. The wave of the electrons actually behave as it tunnels through this vacuum barrier, this potential barrier between the needle and the surface of the sample that we want to image the atoms of. Right, and let me just take a look at this complicated picture and say that very often we will see picture in which a more simplified version of this picture. Right, the way it is simplified is this. This barrier here, instead of this curve that I've drawn, is often, this part here is often redrawn as here. It's often redrawn as a rectangle. Alright, rectangle is always simpler than a curve like this. And this part here, where I have lots of little dips here because there are protons there, are usually just represented by something flat. Just a very rough approximation where the electrons travel in between the protons. Okay, so the electrons does not have to actually see this deep potential all the time. So if it travels in between the atoms in between the nuclei, it wouldn't actually experience the infinitely negative potential all the time. It would just experience a potential that goes up and down. So this is roughly approximate. It might roughly be approximated as a straight line, and this is in a schematic view of the potential. And the wave of the electron itself might be represented this way. Imagine a sine function traveling towards the barrier. When you reach the barrier, it turns into an exponentially decaying function. I'll try to draw this again. Sine function turns into an exponentially decaying function, and when it reaches the other side, with a non-zero amplitude, it will just continue on with the same wavelength but a lower amplitude. And this part here, well, I've talked about how this part can be represented by a sine function here, sine function there, and then this part in between might be represented by an exponentially decaying function. Okay, right. So if we imagine that the incoming amplitude is 1 sine x, and then the amplitude of the wave that comes through here, let's say I call it T for transmitted amplitude. Okay, so that's T for transmitted, for transmission. We might expect a smaller amplitude here. That means it just means that there is a smaller chance that the electron is here than it is there, but there's a finite chance, so that maybe 1 out of some number of electrons there can actually just hop over to the other side. And then and once we have such a possibility, it is possible then on average to have a current, which we call a tunneling current. And as to this function here, let's say the spacing or the distance of this barrier, let's say it is d. So d would correspond to, say, this distance here, which I call d. Okay, that would be this distance here. So because of this function, this exponential function, if you think of x here as let's say x as the distance from this side of the barrier, then we can think of e to the minus k times d as the drop in amplitude when the wave reaches here. So when this x is 0 down here, this is just e to the power of 0 is just 1. But when x is d down here, the amplitude has dropped to e to the power of minus kd. Okay, so this means that we can have an expression for the transmitted amplitude, right? We can even say that the transmitted amplitude T is given by this expression. Now, and then if we take this idea a bit further, if there's a transmitted amplitude, there must be a reflected amplitude. So if we imagine that 1 is the amplitude of the wave coming in, then there must be some that is reflected with the amplitude R. Okay, so there must be a reflected wave that goes back in the opposite direction. So the reflected wave and the incoming wave would add to give you a resultant sine wave, that is as I've drawn here. But we might imagine that if I add up the reflected and the transmitted amplitude, I should get back the total incident amplitude, which is 1. Oh no, I shouldn't be talking about amplitude. Just a minute. I should be talking about the probability, right? The incident probability, transmitted probability, and the reflected probability. So if e to the minus k d is the transmitted amplitude, then I mean if e to the minus kd is the amplitude here, then the transmitted amount, right, or if I think of this as say the probability that an electron is transmitted or the transmission, if you think of it as a probability, then it should be the square of the amplitude, which means that's e to the minus 2 kd. Okay, so we if you are doing A-level physics, you probably don't need to use this formula to do any calculation. So you just need to know about it for your information, and then the transmitted probability plus the reflected probability or coefficient, as it's often called, must add up to 1.